Hello, this is Brother Cromar from the Math Department at BYU, Idaho, and for these videos we'll be covering Lesson 12, which is dealing with inference for one mean sigma unknown, or the population standard deviation unknown. And so for the outline for these videos, we'll be covering the t-distribution. We'll be comparing the t-distribution to the z-distribution. We'll be dealing with hypothesis testing and confidence intervals, and then checking assumptions when we are dealing with one mean sigma unknown procedure. So first of all, let's talk about the t-distribution. Now if you look at the bullet points down below, we use the t-distribution when we don't know the population standard deviation. In fact, here's the formula for the t-distribution. It's x bar, which is sample mean, minus the population mean, divided by, instead of what you saw in lesson 9 where it was sigma, it's s, which is the sample standard deviation, divided by the square root of n. Now if you compare the two different distributions where the red curve represents the t-distribution and the z curve represents the z-distribution, notice here that for the t-distribution, the tails are thicker on both ends and the center is smaller. And the reason for that is that since the population standard deviation is unknown, we have more variability with possible results, and so we'll have more items here on the extremes on the tails. Okay, but notice what happens when we increase our sample size. Now what I have down here is I have something that represents, it's 1 degree of freedom. So this here represents the t-distribution with 1 degree of freedom. In this case, degrees of freedom is their sample size that you get from your sample minus 1. So say the sample size is 2, the degrees of freedom would be 1. Now if we increase our degrees of freedom and turn our sample size, notice what happens to the t-distribution. It becomes closer and closer to the z-distribution. So that's one of the benefits of increasing our sample size, is that we have thinner tails for this bell curve. Okay, so now that's a brief overview, but basically I hope you see the differences between a t and a z-distribution. Now the next thing I want to cover is hypothesis testing for one mean sigma unknown test. So let's review here from lesson 9 the 5 steps with dealing with one mean standard deviation known, or sigma known. We did these 5 steps where first we stated the known alternative hypotheses, and then step 2 is what we computed a test statistic. Now for lesson 9, for one mean standard deviation known, this was our test statistic where we used a z-distribution. And then step 3 is from our test statistic we used an applet to get our p-value. And then step number 4, we went to the decision rule where we reject the null hypothesis if the p-value is less than our level of significance. If it's not, then we don't reject the null hypothesis. And then we state our conclusions. If we reject the null from the last step, then we state in our conclusions we have sufficient evidence to say that, and then we state the alternative in plain English. If we don't reject the null hypothesis, then we have insufficient evidence to say that, and then we state the alternative hypothesis in plain English. So then the question down on the bottom left is, how realistic is the population standard deviation being known? Well, more so than not, we do not know the population standard deviation. So what we covered in lesson 9 and then lesson 10 with confidence intervals, we did that as just to get you started with hypothesis testing and confidence intervals. But now we're going to go forward with dealing with in a real case where we don't know the population standard deviation, so we have to estimate it. So now we're going to deal with 6 steps when we don't know the population standard deviation. And now if you notice here, this step here, the first step is the same where we state the known alternative hypotheses, and the last 2 steps of our steps is also the same where we have a decision rule and we state the conclusions. However, it's steps 2 through 4 that change, where we do compute a test statistic, but now it's a different test statistic where we're solving for t within the t-distribution. We get our degrees of freedom, and as I mentioned earlier, degrees of freedom is your sample size minus 1. And if you notice there, as our degrees of freedom change, so does our bell curve change. The tails get thinner and the center gets bigger when we increase our degrees of freedom. And then we get our p-value. But what's going to be different as well is that now we're going to compute things using Excel or SPSS depending on the class that you're taking. Whereas earlier with what we did was we solved the test statistic by hand and then we got a p-value using the applet. But these steps here we'll be getting that information from either Excel or SPSS. Okay, so let's go through an example of this. So we want to conduct a hypothesis test to determine if the mean body temperature is different from 98.6 degrees Fahrenheit. So say for instance, I didn't include it up here, but say for instance we set a level of significance of 0.05. we do this test. So step 1 is state the null and alternative hypothesis. Well, the mean, the status quo, what we're used to thinking is that the mean is 98.6. The alternative hypothesis, we're looking to see if it's different. So this is a two-sided test. We state it here where the mean is not equal to 98.6. So then we go to steps 2, 3, and 4 where we look at our output either in SPSS or Excel. Now what I'm going to show you is SPSS output. So those of you who are using Excel, you can go through the wiki or ask your teacher in terms of how this is done. But this output is also very similar. This output that I have here in SPSS is similar to what you see in Excel. So here's where you get the results. This is our test statistic. This is step 2. This is our degrees of freedom, and then this is our p-value. Now in this case, notice here that in SPSS it says sig two-tailed. What that means is in SPSS it's a p-value for a two-sided test. If this were a one-sided test, all we'd have to do is take this number and divide it in half. Now in Excel, you guys can mark it in terms of if it's a one-sided or two-sided test. But here in SPSS, you just take this number and divide it in half for a one-sided test. But normally, but SPSS assumes you're doing a two-sided test. Okay, so we go through these steps. So this is our test statistic, degrees of freedom, and our p-value. Now it's said in there as 0, but it's in our output, but it's never 0. There's always going to be some type of probability, but so I'll just say it's close to 0. And so we go to the next step, which is our decision rule. So our p-value, if our level of significance is 0.05, our p-value is less than our level of significance, so therefore we reject the null hypothesis. Okay? So now we have sufficient evidence to say that the mean body temperature is different than 98.6. So in our conclusions, we refer to the alternative hypothesis, but we state it out in plain English. So now let's go through one more example here. Okay, so here is the birth weight of a child is an important indicator of their neonatal health. It is important that pediatric healthcare providers track changes in the birth weight over time. The birth weight of children in Australia has historically had a population mean of 33.73 grams. Is this still the mean birth weight of Australian children, or has there been a decrease? And we'll use the level of significance of 0.05. So first of all, what is the null and alternative hypotheses? Well, the null hypothesis is that the mean is equal to 3,373 grams. And the alternative, since we're looking for a decrease, now this is a little different than what's in the textbook, but I decided to change it up just so that you could see an example with the one-sided test. But this is where the mean is less than 33.73. So then steps 2, 3, and 4 we would get from our output. So I'm just going to go here to some of my SPSS output. This is similar to Excel. And so this here represents my test statistic, which is 1.219. This is my degrees of freedom. So our sample size in this case would be 44. And then our p-value, now remember with SPSS, this is if it's a two-sided test, but now we have a one-sided test, so we divide this number by 2. Like I said, in Excel, you would just click an item in Excel to get your results, to get the p-value. So anyway, the p-value that I have is 0.014. So this is our test statistic, our degrees of freedom, and our p-value. And since our p-value is greater than our level of significance, we do not reject the null hypothesis, and we have insufficient evidence to say that the mean birth weight of Australian children has decreased from 3,373 grams. So this will conclude part 1 of the lesson 12 video, and so when we get to part 2, we will discuss confidence intervals, and lastly we'll cover checking assumptions.